An important concept in electricity, closely related to electrical continuity, is that of points being electrically common to each other. Electrically common points are points of contact on a device or any circuit that have negligible, extremely small resistance between them. The ground or negative connection on a protoboard or breadboard along the bottom in this picture are electrically common to each other, because there is electrical continuity between them. This breadboard or protoboard has two common connection rows along the top and two common connection rows along the bottom for positive and negative power supply connections. Conversely, this breadboard points within a row of 5 holes vertically in this illustration are not electrically common because there is no continuity between them. Continuity describes what is between the points of contact, while commonality describes how the points themselves relate to each other, though those little 5-hole groups are not connected. Many electrical and electronic systems use common connections. Almost all cars use a negative ground connection that is connected to the metal chassis. This effectively uses the car frame itself as the conductor to the negative side of the battery. The negative side of the car battery is connected to the car chassis. The test instrument, an oscilloscope, in this diagram is connected to a common ground with a device under test. This leaves the probe free to check for voltage and signals without having to reconnect the negative or ground connection each time a new measurement is made. The negative probe of this multimeter is connected to the negative ground of this power supply. That leaves the positive red probe free to make measurements with only one hand. Now, let's do some more measurements with our multimeter. Pause the video when you do each step. First, let's select a 1000 ohm or 1K ohm resistor from your parts assortment. This resistance value is indicated by a series of color bands: brown, black, red, and then another color representing the precision of the resistor: gold for plus or minus 5% or silver for plus or minus 10%. Set your multimeter to the 2K range and connect the meter probes across the resistor. What does your meter display? This meter is set to the 2K range, so this reading is kilo ohms or K ohms. So this is 0.992 kilo ohms or 0.992 times 1,000, which is 992 ohms. Try reversing the test probe connections on the resistor. Does this change the meter's indication at all? What does this tell us about the resistance of a resistor? What happens when you only touch one probe to the resistor? Why does the meter not read exactly 1K? Remember, the tolerance is given by the fourth band. In this case it is gold, which means 5%. 5% equals 0.05. 0.05 times 1,000 equals 50. So this resistor resistance should be within 1,000 plus or minus 50 ohms, or 950 to 1,050 ohms. So the resistor in this picture is within tolerance. Is yours? Try changing the settings on the meter. What happens when you select a range higher than 2K? What happens when you select a range lower than 2K? Now select a 10,000 ohm or 10K resistor from your parts assortment. This resistance value is indicated by the color bands brown, black, orange, and then another color representing the precision of the resistor: gold plus or minus 5% or silver plus or minus 10%. Set your multimeter on the 2K range, unless it's multi-ranging. Connect the meter's test probes across the resistor and note its indication. Why does the meter display that? Now try changing the meter range to 20K. This time you should get a reading. The resistor measures 9.82K in this picture. Kilo means 1,000, so this is 9,820 ohms. Why is it not exactly 10K? Remember, the fourth band means that this is within 5%. Is this resistor within tolerance? 5% equals 0.05. 0.05 times 10,000 is 500, so this resistor should be within 10,000 plus or minus 500, or 9,500 to 10,500. So the resistor in this picture is within tolerance. Is yours? Try a 100K resistor. What range do you select for your multimeter? Is your reading within tolerance? When you touch the meter probes to the resistor terminals, try not to touch both probe tips with your fingers. If you do, you will be measuring the parallel combination of the resistor and your own body, which will tend to make the meter indication lower than it should be. When measuring a 10K ohm resistor, this error will be minimal, but it will be more severe when measuring higher values of resistor. How does touching both probes affect the 100K ohm measurement? Now try some more resistors. Read the color codes. Be sure to select a range above that which you expect. Are they within tolerance? You may safely measure the resistance of your own body by holding one probe tip with the fingers of one hand and the other probe tip with the fingers of the other hand. Note, be careful with the probes as they are often sharp. Hold the probe tips along their length, not at the very points. You may need to adjust the meter range as your body resistance tends to be greater than 10,000 ohms. Try wetting your fingers with water and remeasuring the resistance with a meter. What impact does this have on the indication? Resistance is the measure of friction to electron flow through an object. The less resistance there is between 2 points, the harder it is for the electrons to flow between those 2 points. Given that electric shock is caused by the large flow of electrons through a person's body, and increased body resistance acts as a safeguard to making it more difficult for electrons to flow through us. What can we ascertain about electrical safety from resistance readings obtained with wet fingers? Does water increase or decrease shock hazard to people? Measure the resistance of a rectifying diode with a multimeter. Reverse the test probe connections to the diode and re-measure the resistance. What strikes you as being remarkable about the diode, especially in contrast to the resistor? Take a piece of paper and draw a very heavy black mark on it with a pencil, not a pen. Measure the resistance on the black strip with your meter, placing the probe tips at each end of the mark. Remember to try different ranges on the meter. Move the probe tips closer together on the black mark and note the change in resistance value. Does it increase or decrease with decreased probe spacing? If the results are inconsistent, you need to redraw the mark with more and heavier pencil strokes so it is consistent with its density. What does this teach you about resistance versus length of a conductive material? A photoresistor or photocell is a resistor that changes resistance depending upon the amount of light hitting it. They are sometimes called light-dependent resistors, LDRs. The Electronics Learning Lab has a photoresistor in the upper right-hand corner. Connect your meter to the terminals of a photocell and measure the change in resistance created by differences in the light exposure. You may want to use an alligator clip jumper wires to make the connections with the component, leaving your hands free to hold the photocell to a light source and or change the meter ranges. What happens when the light hitting the photoresistor gets brighter? Darker? Measure the resistance of a glass of water. Keep the probes spaced the same and at the same depth when you compare the measurements. What happens to the resistance when you add salt to the water? The inverse of resistance is called conductivity. As the resistance of something goes up, the conductivity goes down. Sometimes it is more convenient to talk about conductivity of something. A wire should have high conductivity and low resistance. Pure water has high resistance and low conductivity. Conductivity measurements are a good way to see if water is pure or polluted. Experiment with measuring the resistance of several different types of materials. Just be sure not to try measuring the resistance of anything that produces substantial voltage like a battery. Suggestions for materials to measure are fabric, wood, plastic, glass, diamonds, paper, wet or dry, oil, and rubber, and other things. Now that you are familiar with your multimeter, you will find it to be a powerful tool that allows you to measure electric current, voltage, and the resistance of devices or objects. It is one of the most important tools for testing and troubleshooting electronic devices and circuits.